Understanding the magnitude of correlation for sample means for correlated random variables. This presentation is based on our publication titled Evaluating the Correlations of Cost and Utility Parameters from Summary Statistics for Probabilistic Analysis in Economic Evaluations. I thank my co-authors. The SARS and R code for the examples can be found in the appendices of this article. In Appendix 1 of our article, we provide proof of the magnitude of correlation for sample means for correlated random variables. This slide showed the proof that for correlated random variables x and y, the correlation coefficients of sample means and samples are equal to one another when x and y are drawn jointly. When samples of x and y are drawn independently, the correlation coefficient of sample means is equal to 0. Now, I will introduce implications of the proof. In probabilistic analysis, researchers use the distributions of parameter estimates, distribution of sample means, such as normal distribution with sample mean and standard error for continuous variable, and beta distribution for binary data, as model inputs to capture the parameter uncertainty. While the distribution of samples, individual patients, can be used as model parameters for microsimulation analyses, normal distribution with sample mean and standard deviation for continuous variable, and Bernoulli distribution for binary data. Then, if we obtain the estimate of the samples or sample mean, we can use this estimate in probabilistic analysis and/or microsimulation. If model parameters are obtained from different data sources, independent sampling, there are no correlations between these parameters. When different model parameters are from the same sample and the correlation coefficients of the sample are reported, we can directly use these correlation coefficients to simulate correlated distributions of sample means in probabilistic analysis. Based on the central limit theorem, we can simulate multivariate normal data for correlated model parameters during probabilistic analysis. Now, I will introduce the method of detecting and quantifying the correlations between variables from summary statistics. When correlation coefficients are not reported, it is possible to calculate them based on the summary statistics. The mean and variance of the linear combination of two jointly distributed random variables x and y were expressed in this slide. We can use the following formula to calculate the covariance and correlation coefficient. To contextualize this formula, we can assume that x and y are the numbers of general practitioner and specialist visits, respectively, and b are the unit costs, the constants, for general practitioner and specialist visits, respectively, and ax plus by is the total cost of physician visits. I will now present the example 1, non-severe and severe hypoglycemia events. This study reported means and 95% confidence intervals of the incidence rates of total hypoglycemia, non-severe hypoglycemia, and severe hypoglycemia events. We can calculate standard errors from 95% confidence intervals and derive the covariance and correlation coefficient between the incidence of non-severe and severe hypoglycemia events. We calculated that correlation coefficient was equal to 0.19. We simulated multivariate normal distribution data for probabilistic analysis based on the estimated means and standard errors to address the uncertainty from the parameter estimates. This slide showed the summary statistics of the simulated data. We also simulated correlated Poisson distribution data for the counts of non-severe hypoglycemia and severe hypoglycemia events in hypothetical individual patients in microsimulation to capture individual variability. In addition, The probabilistic analysis and microsimulation are sometimes also referred to as second-order and first-order Monte Carlo simulations, respectively. Example 2. An economic study reported the means, standard deviations, of total costs and breakdown of costs in 5 categories: inpatient, emergency department, outpatient, home health care, and other, over a 12-month period for patients with diabetic foot ulcers among Medicare beneficiaries in United States. We found that the sum of variances of the 5 cost categories was about 50% of the variance of total costs, which indicates that considerable positive correlations existed among different cost components. The correlation matrix of the 5 cost components includes 10 unique correlation coefficients, and the exact values of these coefficients are unknown from the summary statistics. It should be noted that the magnitude of the correlation between cost components does not impact the variances of individual cost components, only the variance of total costs. Given that our main goal of incorporating the correlations between cost components is to properly understand the variance of total costs, we can assume that there is a common correlation coefficient for all cost components. We can then simulate multivariate normal distribution data, using means and standard errors, of 5 cost components with varying values of correlation coefficients, ranging from 0 to 0.5 by 0.05. In this case, when the common correlation coefficient was 0.25, the standard deviation of simulated total costs was 234.9, which was close to the standard error of total costs, 236.6, in the observed data. The precision of the estimate of the common correlation coefficient can be improved by running more simulations. In the present study, we used the simulation approach to approximate the correlation coefficient. We provided the analytic solution in another article under the assumption of the common correlation coefficient. Thank you.